Section 4.7 on antiderivatives, page 2. Now, one of the keys to taking antiderivatives is you always want to begin by rewriting or simplifying the question, just like we do whenever we take a derivative. We want to make sure that it fits our formulas. And also, when it comes time to take the antiderivative of a power rule problem, I personally think it's easiest if you find the exponent first and then put the reciprocal out front. What I'm referring back to is a lot of people look at this formula, and since we read from left to right, they want to start here. But I think once you start with the exponent first, then you know what is the denominator of your reciprocal. And upon further inspection, let's go ahead and start with problem C. I think it's actually the easiest one. The directions are to find the most general antiderivative. The reason they say most general is we're going to get answers that end in plus C. But as you're going to see later on, we can actually find answers where we don't have plus C if we can solve for that constant. But I'm getting ahead of myself. Example C. I see 6x to the fifth. I could take a derivative of that. It's in the right format. 6x cubed, I could take a derivative. 17, I could take a derivative. I don't need to rewrite this to take derivatives, so I don't need to rewrite this to take antiderivatives. I take, in what I wrote in dark blue, 6x to the fifth and copied it down here. Now I'm going to add 1 to the exponent first, and then that is going to become my denominator. Next I have minus, and then my 6x cubed, where I'm going to add 1 to the exponent and take that new exponent, it's kind of hard to see the way I wrote it, to be my denominator. Plus 17 stays here, but remember that's a scalar. So since we're using the variable x, I get to just stick a single x there, and then we end in plus c. So just kind of looking back, I used rule 1 and then rule 3 where I had a constant. The only thing left to do is kind of simplify, right? I should have said 5 plus 1 is 6, and so I'm dividing by 1/6. But in our case, we already had a constant of 6, so I can simplify those to just get x to the 6th. My 3 plus 1 became a 4, which becomes a denominator. And so since the 6 in front was really like over a 1, I can divide the numerator and denominator by a 2 to simplify this to the fraction of 3/2 to write out front or as part of my term. Plus 17x, I don't need to do anything. Plus c, I don't need to do anything. And now I've got my antiderivative. Since I had lowercase f, I'm using capital F for my antiderivative. But remember, I can check if I have the right answer by taking the derivative. The derivative of x to the 6th is 6x to the 5th. Leaving that minus 3/2 out front, the derivative of x to the 4th is 4x cubed. And of course, I can simplify a 2 in the denominator with the 2 in the numerator. 17x becomes just 17. And plus c, well, it's a constant, so the derivative is 0. So I've got my 6x to the 5th, and multiplying is going to give me minus 6x cubed plus 17. Notice that this is the question, so I checked my answer. Now, what we were saying, though, is sometimes you're going to need to simplify the question. This looks like it would be a quotient rule, but I'm lucky. I'm dividing by a monomial. So this doesn't look like any of the formulas that we were given because I need to simplify first. Whenever you have a monomial in the denominator, you can then divide every single term by that monomial and simplify. Each term, in this case, I'm going to go ahead and leave this middle term with 1 over x, or you could have written this as x to the negative 1, but I definitely want to write x to the negative 2 for the last term. So I've taken this simplified form. So I have lowercase f of x. The question is identically what I just underlined. To integrate, I keep my x squared. I add 1 to the exponent and make this 3 a denominator. I just have a constant of minus 8. So by rule 3, you can just stick your variable. We're using x for our variable in this case with the piece. If I have the special case of 1 over x, which is also x to the negative 1, then rule 2 says, oh yeah, don't forget it's the natural log of whatever variable you're using. And keeping that minus sign and adding 1 to the exponent, I get negative 2 plus 1, I get a minus 1. Don't forget, I'm always including plus c. So I just simplify any of the math that I can do, which doesn't really happen till over here, right? I've got a minus 1, and because I have minus a minus 1, we change that to a plus, and then I went ahead and moved this back to the denominator. Again, you could take the derivative. Now keep in mind the derivative is not going to look like the question. The derivative will look like the simplified form that we were working with. And then we've got all those other rules we looked at. Rule 7 said if you have a variable that's in the exponent and it is not base e, then you take the question all over the natural log of just the base. But if you did have base e, you're going to leave the question, and whatever k was, you're going to have 1 over k. And then don't forget, we also had that scalar multiple that just kind of stays there. And this is really 10 over 1. So I have a 10 in the numerator I can divide by 2, and a 4 in the denominator I can divide by 2, and I need my plus c. So again, taking the derivative of this would get me identically back to the question. And then we've got those trig functions. I've got this 2 that's going to stay there, but when I take the derivative, the antiderivative of the sine of x, I get negative the cosine of x. I've got minus, but the antiderivative of secant squared is tangent, and I can't forget my plus c. And just be careful that this doesn't look like 2 subtract cosine of x. Remember, you need to multiply 2 and what's really a negative 1 to get negative 2. Okay, now I was mentioning sometimes our answer will not end in plus c because we're going to be given what are referred to as initial conditions so that we can solve for that c. So just restating, we won't answer plus c because we're going to find some sort of value that is c. And one other thing to notice on this particular problem, they gave us a question that's f double prime. So a single f we assume is the derivative, but they notated that this is the second derivative, so I'm going to have to integrate twice to get f. I know I want f because my 2 initial conditions just have f here. If I had had an initial condition like f prime of 0 equals 10, whatever it may be, then I would only need to take the antiderivative, also referred to as the integral, once, so I could use that initial condition. But both of these initial conditions are down to the original. So I am going to copy this question over here for clarity, and I'm going to take the antiderivative. If I have e to the k times, well, apparently we're using t for our variable here, then k is 1, so I have 1 over k, and that coefficient stays there, just like the coefficient of plus 3 stays here, but the derivative of sine of t, using my rules above, is negative cosine of t, and I still do a plus c until I've solved for it. So really, I don't look like I've done much to the first term, but again, multiplying that 3 with a negative sign gives me minus 3 cosine of t plus c. But I don't have initial conditions with a f prime, so I need to take the antiderivative again. My e to the kt, where I think of it as k being 1, goes to a denominator, and that 2 coefficient stays there. So I just have, again, what looks like the question. But my minus 3 stays here. Cosine of t has an antiderivative, sine of t, and then I need to integrate c. Remember, I'm treating c like it's a constant. My variable is t, so it would, instead of being c of x, it's c of t, and I need a new constant when I take the antiderivative, because the derivative of this would lead to a plus 0 if I was checking my answer. So I now have an antiderivative from the second derivative question, and I am going to solve for C and D. So let's look at that. Step 2, I've got 2 pieces of information. Usually when you have an input of 0, you want to use that first because it's going to knock out a lot of the math. I'm taking that answer I just got, and wherever t was, I'm putting a 0. And in this case, it equals 0. Maybe it equals 17, I don't know. But in our case, it equals 0. Don't forget, anything to the 0 power is 1. So I just have a 2 here. The sign of 0 is 0. So negative 3 times 0 is gone. My constant times 0 is gone. But my constant that is not multiplied by anything is there. So I'm just left with 2 plus d equals, well, in this case, we were told equals 0. So I can subtract a 2 from both sides to get d is 2. So I can come back to that formula, and where d is, put a minus 2. Now I'm going to use the second piece of information, that if pi was my input, and wherever t was, I put pi, I'm going to set this equal, well, in this case, they told me to 0. So I can't simplify e to the pi. I do know that the sign of pi is 0, and negative 3 times 0 is gone. I can't simplify c times pi, and that constant of minus 2 stays there. Remember, pi is not a variable, only c is a variable. So I'm trying to solve for c by subtracting the 2e to the pi over. This was gone. I can add the opposite, which would be a positive 2 to the other side. And now, to take this and solve for c, I'm just going to divide everything by pi. So I need to go back to that answer I had, 2e to the t, minus 3 sine t. And where I had c times t, I found this crazy looking thing for c times t and plus d, but we had found d to be negative 2.